What's going on? Good morning. Good morning. Monday morning. What's new? Chat. Don't know how many people are actually there. The one viewer could be myself. So I don't know if anyone's actually watching. Is anyone there? Hello, hello. Did everyone stay up till like 3 a.m.? And that's why no one's here? All right, well, just so for people can view it later, I'm just going to go over some of the topics. Hey, good morning, Jocelyn. I hope you had a really good weekend. I hope you didn't have any troubles with taking the test and things like that. Hopefully you found it very easy. That's the dream. That's the dream. But in last night's lesson, we went over compositions. And composition of functions is essentially we're just taking the value or the function and you are plugging it into another function. So for example, on number 1, if my f of x is x squared and my g of x is 2x plus 1, if I ask what is g of f of 0, the way that our brain should visualize it is this. So it's saying take 0 and plug that into your f function. Then whatever that is gets plugged into your g function. So let's start with that first part, f of 0. Well, that's 0 squared. So f of 0 is 0. So I'm replacing that with 0. So then I'm finding what g of 0 is. And that's 2 times 0 plus 1, which is 1. So my answer, if I say what is g of f of 0, that's going to equal 1. And it's always, I guess if you look at it this way, we're taking the 0, we're plugging it into f, and then whatever that is gets plugged into g. I like visualizing it this way. So I take whatever expression it is, and I rewrite it that way, and that makes it much easier for us to kind of visualize how things are getting plugged in. Let's look at another one. Let's try f of 2. And my f function is x squared. So this is the same as f of 2. So take 2, plug it into my f function, whatever that is, plug it into my f function. So plugging in 2, you're going to get 4. So now I have to take 4, because this right here is 4. So now I got to take 4 and plug that into my f function. So my f of 4 is going to be 4 squared, which is 16. So then I can say f of 2 equals 16. Comments or questions on that? For number 3, very specifically, the only thing that's different is now you have fractions. And so it's just messy simplifying fractions, but just use a calculator. You know, you can plug all that stuff into our calculator and simplify it. So we don't need to overcomplicate it with the fractions. But essentially, problems 1, 2, and 3, it's all the same thing. We're just plugging them in like a function composition. Any questions on 1 through 3? Okay. So let's start moving on to 4 and 5. So with 4 and 5, very, very similar. The main difference is we're now looking at abstract functions. So before, we were taking values and evaluating. In this instance, we're leaving them in terms of x. And sometimes, you know, that can get a little difficult when we're just leaving them in terms of x. So let's look at number 5. And let's do the first one, g of f of x. So the way we look at it is g of f of x. So it's saying take your f function, which is f of x, and plug that into your g function. So if my f function is 3 minus x squared, that means I need to take 3 minus x squared and plug that in for x into my g function. So if my g function is the square root of x plus 1, that means instead of x, I have 3 minus x squared. And then you can simplify that. That's 4 minus x squared. And so this right here is g of f of x. Because remember, this right here, and I'll kind of draw it in green, this was the x. And I replaced that x with the f function, which was 3 minus x squared, and then plus 1. Comments on that? Okay. So then the next part, it says state the domain and range. So in our domain, there are 3 restrictions. We've only gone over 2 of them, so we're only going to worry about 2 of them so far. The first was rational. Are we dividing by x? No dividing by x there. The second is anything inside of a square root, because we can't have a negative inside of a square root. That violates our domain. And so in this instance, I have 4 minus x squared inside of a square root. So I'm going to say that 4 minus x squared has to be greater than or equal to 0. That's our mathematical way of saying we're not making it negative. And so I want to solve for this. 4, I'm going to add x squared to both sides. And so you're going to get x equals, if I take the square root, plus or minus 2. And so that's going to be on a number line. -2, +2. It can equal it. So close circle. And then now I just need to test true or false or use a sign chart. It doesn't matter. This symbol here is positive numbers because they're greater than or equal to 0. So we only want positive. So if I plug in -3, I get 4 minus 9. That's -5. It's negative. If I plug in 0, I get 4 minus 0, which is positive. If I plug in +3, 4 minus 9, it's -5, so that's negative. We're looking up for positive numbers, so that's our solution. So my domain is going to be from -2 to +2. Now, the only way for us to really find what our range is going to be, that's going to be by taking this and plugging it into a graph. So plug that in. like y equals the square root of 4 minus x squared. So all I got to do is just plug that into a graph. But for your range, it should be from 0 to 2. Let's verify that. It says that I'm lagging. Am I lagging? It'll be the first time that it's all being laggy if that's the case. So here it is, 4 minus x squared, and it's from, the range is from 0 and it goes all the way to 2. All right, any questions on 4 or 5? Number 4 is a little bit easier than number 5. I'm hoping that from integrated 3, we're used to doing a lot of that. We've probably seen some of this in the Alex. Okay, let's move on. So numbers 6, 7, and 8 are all actually very, very similar to these first ones. The difference is, instead of expressing it in functions, we express it as a graph. So for example, in number 6, we have g of f of 1. So remember, the way we visualize this is by saying g of f of 1. So I'm taking 1 and plugging that into my f function. So I need to look at my graph here, and my f function is the left one. Well, at 1, it gives me 2. So f of 1 is 2. So that means instead of f of 1, I now have 2. So now it says, what is g of 2? So now I look at my g function, which is the right one, whereas 2, and I go up, and there's 3. So g of 2 is 3. So then g of f of 1 equals 3. And that's going to be my answer there. For number 7, take 3 and plug it into your g function. So if I, at 3 in my g function, it's 0. So then I take 0 and plug that into my f function. So if I plug 0 into my f function, that's the left one, at 0, it's 4. So for number 7, it should be 4. F of g of 3 equals 4. Any questions on that one? Okay. Let's move on. Number 9 says graph and state all of the elements, including the end behavior. Ooh, so we're doing everything on this one. Okay. Let me give myself some more room here. All right, so I have 2x squared minus 3x minus 5 over x squared minus x minus 6. All right, so let's see if the top factors. So a times c, I get 10. What factors of 10 can add to 3, 2, and 5? So that means that factoring so I want to get a -3. So this should be let's verify that. 2x and x give me 2x squared. The -5x plus 2x gives me -3x, and then -5 and 1 give me -5. Okay, so that's factored. And then the bottom, this factors into x minus 3 and x plus 2. Let's verify that. X times x gives me x squared. -3x and 2x give me -x. And then -3 and the 2 give me the -6. Now, the reason why I factored it is I'm trying to look for, are there any points of discontinuity? And so in this instance, there are no points of discontinuity. So we're good there. So I don't have any holes. Then my vertical asymptotes. So set the denominator equal to 0, so you're going to get x equals 3 and -2. Then the horizontal asymptote, my degrees are the same, 2 and 2. So then we divide the leading coefficients, so 2x squared over x squared. So my horizontal asymptote is y equals 2. Now, just to kind of save a little bit, I'm going to put everything, all those important pieces on the graph here, but then we're just going to kind of use Desmos to kind of help us plot those points. It just saves us time. 1, 2, 3, and then -2, and then +2. So the purple, there's our horizontal asymptote, and then our vertical asymptote is here and here. Now for me, I would pick x in my xy tables. Technically there's only one, but I don't have room. That's why I just drew 2. I would pick values on this side of my vertical asymptote. So that would be values like -3, -4, and -5. I would pick values in between those two vertical asymptotes, and you may have to end up picking more. So I would pick -1, 0, 1, and 2. Like I said, you might have to pick more. You might have to pick -1/2, and you also might have to pick 2.5. And then picking values that are going to be greater than that, I'd pick values like 4, 5, and 6. And I would take those and you just plug them into your function. So you take that and you take those values and you plug them in for x and you simplify it. Now, like I said, just to kind of save some time, so we're not just spending all the time in the world plugging those in, let's just take a look at the graph. So 2x squared minus 3x minus 5. And then on the bottom, x squared minus x minus 6. So this is what my graph looks like. If you were to take everything and plug them in, you should be able to get a nice sketch of what this graph is. Any comments or questions, anything that you guys want me to go over a little bit more in depth on this? So that last little bit, the end behavior, let's kind of go over that. Let me shrink this down just a little bit. Actually, I'm just going to new page. There we go. Okay, so if that's our graph and that's the graph that we drew, I see x doing multiple things. So we basically have to look at, in behavior is always any instance my graph is going to infinity. So it's going to infinity here. It's going to infinity up here. It's going to infinity down here and down here and up here and right here. So there's 1, 2, 3, 4, 5, 6 places where my graph is going to infinity. Those are all important values that we need to basically state for our end behavior. So in this instance, my x is going to negative infinity. So I'm going to say x is going to negative infinity. In this instance, my x is going up forever, my y is going up forever, so that's going to infinity. And what x value do we assume? That's going to be 2. So we have x is going to negative 2, and we have to state what side, so from the negative side. And then it's also going to infinity down here. So once again, x is going to negative 2, but this time it's from the positive side. And then it's going to negative infinity down here. That x value is 3. So x is going towards 3 from the negative. And then it's also going up here. So that's also the value's 3, but that's from the positive side. And then the last one is it's going to infinity here, and so x is going to go to infinity. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so now all we have to do, so we stated everything that x is doing. Now we just have to state what the y is doing in association to that. So when my x is going to negative infinity here, my y value is going towards 2, which is the horizontal asymptote. When my x is going to negative 2 from the negative side, my y value is going to positive infinity. When my x value is going to negative 2 from the positive, so that's this one right here, it's going down forever. So my y value is going to negative infinity. Now the same thing for this one. And then when it's going towards 3 from the positive side, it's going up forever. So it's going to go towards positive infinity. And then as x goes to positive infinity, my y value goes to 2. And so that's in behavior. That's a lot. But basically, like I said, it's just every single instance that my graph is going to infinity in some. Last one. Find all the zeros of the polynomial and then completely factor it over real numbers. So when we're finding the zeros of a polynomial, those are our p's over q's. So I have this 8x to the 4th plus 50x to the 3rd plus 43x squared plus 2x minus 4. So we do our p's over q's. So the factors of 4 over the factors of 8. And so we can create our list. So that's going to be 1, 1/2, 1/4, 1/8, 2 over 1, 2 over 2, no, 2, and then 4. I think that's it. Because the rest of them, if I match it like 4 over 8, that gives me 1/2. 4 over 4 is 1. 2 over 4 is 1/2. Yeah, I believe that's it. We have them all here. Let me get rid of this Desmos calculator. And so now what we have to do is we want to use synthetic division. and we go through and we want to test to see which of these are going to be our zeros. Looking at it, I only see one change of sign. So because there's only one change of sign, there could be a positive 0, which is a good thing. Trying to think. What other values could we possibly use? So let's kind of start trying some values out. Let's try 1. So 8, 50, 43, 2, and -4. Add, multiply, add. Okay, so immediately when I see that, it looks like if I just keep doing that, the value is just going to keep getting bigger and bigger. That's not going to be very helpful. So I actually need, for it to get negative, I need my value to get smaller. So maybe it's going to be 1/2. So 8 multiplied by 1/2, I get 4. I get 54. Multiply by 1/2. That's going to give me 27. That still doesn't look like that's going to kind of like get smaller quick enough. So I don't think that the 1/2 is going to be good. Let's try 1/4. So add, multiply. So 8 times 1/4 is 2. Add 52. Is 52 divisible by 4? It is. It's 13. Okay, so then add those. So this looks like it is getting smaller-ish. It's definitely not getting that much bigger. And I think this is where we're going to see kind of like the difference here. So 54 times, 56 divided by 4, that's going to be 14. And then add, and then multiply. Okay, so the 1/4 ends up working. Wow, wow, wow. That's kind of crazy. What else can we use? So I have 1/4. Sorry, x minus 1/4. And then I'm left with 8. So your remainder, constant, x squared, x cubed. So I have 8x cubed plus 52x squared plus 56x plus 16. And then because this is a 4, that means there's a 4 that's factorable out of all of those values there. So I'm going to factor out that 4 just to make it easier. So 4 times x minus 1/4. And then I get 2x cubed plus 13x squared plus 14x plus 4. And then I can multiply this 4 through, and that's going to give me 4x minus 1. So I have that. Let me go back to the original problem. It says find all the zeros and then factor completely. All right, so what I'm left with is 2x cubed plus 13x squared plus 14x plus 4. Those are all positive. So because those are all positive, that tells me that I'm going to have 0 positive zeros. So there's not going to be another positive 0 within that system that's going to be beneficial to me, and it's not going to help me at all. So we can try the negative zeros. Just looking at the values like -1. Well, let's try it. Let's try -1 and see what happens. Because now I'm second guessing myself. So add, multiply, add. Okay, yeah, that's never going to work. Because how do I get 14 down to 4? The problem if I use a 2 or a 4, these numbers are so closely together that if I use a number like 2 or 4, things are going to start doubling a lot. So I don't think a 2 or 4 would work. Maybe it's -1/4. Let's start with the 1/2 first. So 2, okay, nice. This is going to work out nicely. So -1/2, that's going to give me -1. Add those, you get 12. Multiply, you're going to get -6. Here it is. This actually ends up working. Nice. Yay. Okay. Very, very nice. So we're going to get 4x minus 1. And then I'm just going to factor out the 2 here. So remainder constant x squared. So that's 2x squared plus 6x plus 4. And I'm going to multiply that 2 into that factor. So that's going to be 2x minus 1. And then I'm going to get x squared plus 6x plus 4. Now that doesn't factor. So I'm going to have to use the quadratic formula for that. So negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. This is a long problem, man. And then you get -6 plus or minus. Just want to make sure I'm not blocking it. So this is 36 minus 16. So 36 minus 16, that's going to be the square root of 20. And then the square root of 20, that's going to break into 2 root 5. Your square root of 20 is 4. Root 4 is 2. And then you're left with a... So we have -6 plus or minus 2 root 5 all over 2. The 2 is going to cancel out from all of that. So you get -3 plus or minus root 5. Wow, 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 wow. So we got all the zeros. So let's make sure we're answering this question correctly. So it says find all the zeros of the polynomial. So I'm going to say my zeros are 1/4, -1/2, -3 plus root 5, and -3 minus root 5. Good, I'm not blocking it. And then it says factor over the real and complex. So they're going to end up being the same factorizations, but, and I'm running out of room, so I'm just going to explain it. You're just going to do x minus your 0. So in this instance, it's going to be x minus 1/4, or you can write it as the 4x minus 1, and then the 2x minus 1, and then this was x minus -3 plus root 5, and then x minus -3 minus root 5. And that's for the both real and complex, because those values, a square root is still a real number, so we can include it as a real factorization. It's just not a imaginary number. So that's why, and complex numbers are both real and imaginary, so they're going to be the same thing for both. And so an example of how you would write one of those would be x minus -3 plus root 5. right? So like that's would be the factorization of that 0 there. Wow, this is a big problem. I think that problem took like 10 minutes alone. Okay, so any questions on any of what we went over? Are there any of these would you like me to go back and take a look at? Cool. I think we're done then. Yep. All right. So we're done. Thanks for showing up, guys. It was awesome. And I believe tonight is supposed to be 81-2. Yep. Sorry, not 81. 80-2. So go ahead and work on 80-2, finish up the DI. I will open up those slots in Google Classroom as we speak so you guys can get those in. Other than that, I think we're good. Have a good day. Thanks for showing up again. Stay safe, stay healthy, and I'll see you guys tomorrow.